Okay, dear colleagues, it's high time to start our seminar. And as if you missed it or if you were unable to understand Russian, as Pavel said today we will be time traveling with metamaterials to 2008, 2009, and this will be a sort of overview of how the metamaterials development in our department and back then started, and what were the first or maybe the initial results of the things that turned out now into many applications and many dissertations of many PhD students and master students and maybe even doctors, I don't know. So with that, I think we have quite enough of participants. I'll give the right of the talk to Pavel, and if you have any questions, just raise your hand in Zoom or type them in chat. I'll ask Pavel at some point to answer them. So Pavel, welcome.
Misha, thank you for introduction. Indeed, I decided to make some really time travel today. So I will be showing you the presentation which I was presenting in back 2008, 2009 at many places and many conferences. Kind of at least part of it was presented at some conferences. This is about a so-called canalization regime, which we actively developed at that moment. And I decided even to do not modify the front page of the presentation, because really kind of most of results were obtained before I returned back to Russia from Britain. Most of the results were obtained when I was with Queen Mary University of London. So it's completely correct affiliation, not for the current status of mine, but for the results which I will be presenting. And I also have kept this crazy title. I announced canalization of subwavelength imaging, but actually I was given this presentation with this long kind of name, yeah, magnification, demagnification, and transmission of images with subwavelength resolution at microwave, terahertz, infrared, and visible frequency ranges. So it's supposed to give as wide as possible kind of view on what we were doing at that moment. And it's indeed kind of review presentation of what we have obtained by 2009. Co-authors here are actually Mario Silveira. Since that time, he moved from University of Coimbra in Portugal to University of Lisbon, and we continue to work with him actually. George Polikaras moved from Queen Mary, and he is already big boss of Metamaterials Corporation in Canada. He is using metamaterials, kind of selling applications of metamaterials for different purposes. Pekka Ikonen, who was contributing quite actively from Finnish side, from Helsinki University of Technology. Since that time, he was working for Nokia till the moment when Nokia disappeared, and now he left from our scientific research area, and he is just a businessman manager in large Finnish company. Jens Zhao used to be a postdoc in Queen Mary University of London. He's now a professor in Thailand. He married a nice lady from Thai royal family, and he's enjoying his life in Bangkok University as a professor. Konstantin Simovsky and Sergei Tretyakov, they remains to be in Helsinki, but since that time, Helsinki University of Technology changed the name to Aalto University, and they are currently with Aalto University. And professors Jan Hau and Clive Parini are still with Queen Mary University of London. And over here, I have to kind of show you the symbol of Queen Mary. This is a crown, which you can see at the logo of the university. It's very, very important for the presentation. Please keep this in mind. Otherwise, you will have some additional questions. All right. The goal of activity which I will be talking today about, is beating of diffraction limit. So basically, it's a fundamental problem that conventional imaging systems, such as any lenses, microscopes, or whatever, created from lenses, is restricted by diffraction limit. So basically, details which are much smaller than the wavelengths of light or illumination, if you're working at microwaves, cannot be resolved. And this is actually, this restriction holds at any frequency range. If you have microwave lens, you have the same restriction in terms of the wavelengths as if you have optical lens. So this is really fundamental problem. And problem comes from the fact that actually lenses operate with propagating waves, with light, which travel through space or dielectric. And evanescent waves, they decay in free space and in dielectric. They carry information about details which are smaller than the wavelengths. They simply cannot pass through dielectric or vacuum. And that's why they happen to be lost on the way from the source to the image. Yeah. And this is what the people are trying to solve, actually, with the help of metamaterials. Over here, I would like to show you the slide with, I think, one of the really first definitions of the metamaterials. In 2008, there was a metamorphose network, European network of excellence created. Right now, you know this network, actually, they were working during 8 years with two funding by a European agency, and right now they still continue to work. They organize Metamaterials Congress since that time. And this is actually the definition of metamaterials: artificial electromagnetic multifunctional materials engineered to satisfy prescribed requirements. And the properties of this is dictated by basically what is inside of this material rather than materials. And actually at that moment, mainly people were thinking about materials with negative epsilon and negative mu as metamaterials. In this presentation, I will give you a definition, and I will make some introduction to canalization principle. I will tell you kind of small story how we with Konstantin Simovsky invented this nice term. Actually, it's not very good one, yeah, because maybe channeling was better, but canalization is still kind of very fundamental. It has nothing to do with leakage of some bad things from the tap. Yeah, it's really channeling in a sense, but it's canalizing from one side to another side the images. And this will be done without negative refraction and amplification of evanescent waves. So basically without metamaterials with negative epsilon and mu. And I will show you that we can do it in nearly all frequency ranges, probably except X-rays and something highly visible. And I will show you also some results about Hyperlens. So we can not only transfer images with sub-wavelength resolution, but also magnify and demagnify the images. So story starts from a very interesting proposal of Sir John Pendry, who proposed to consider a slab of material with epsilon close to -1, mu close to -1, and as a result, index of refraction close to -1. In this material, you can have negative refraction without any reflections, and you can have amplification of evanescent waves, as you can see over here. So as a result, if you place some source next to such lens, you can get in the plane of the image exactly the same distribution of the field as it was in the plane of the source. But okay, so this is working only, of course, for planar objects, because the image location is dictated by source location, by simple formulas, as you can see here, that actually distance is double distance between source and image is double thickness of the lens. And if you take a look at this, okay, I'm not going to tell bad stories about left-handed metamaterials. The badness is because actually nobody was able to create them without losses, and the problem is that as soon as you have any losses in these materials, this negative refraction and amplification of evanescent waves are no more working, and the perfect lens appears to be a very bad lens. But if we take a look at this as an ideal device, this is actually a perfect transmission device, and we will try to make this perfect transmission device using alternative wave. But what is perfect transmission device? For arbitrary waves coming from one side to this device with arbitrary angle, they're passing through without any changes. So it means the transmission coefficient through device is equal to 1, and also important to have no reflection at all. So for any angle of incidence, transmission 1, reflection is 0. Importantly, slab of free space, it's not a perfect transmission device because evanescent waves do not pass through. Yeah, so only propagating waves are passing through, but also they accumulate some phase. So also transmission coefficient is not exactly 1. So, but perfect transmission device, it's something which transferring field distribution from plane to plane, 1-to-1, yeah, without any modifications. So transmission coefficient is 1. Also very important to have 0 reflections, because if you would like to see some tiny details which are much, much smaller than the wavelength of light, it's important to do not modify these fields. And as soon as you have a lens, placing it next to your object, if certain reflection appears, then you already see not original distribution of the field, you see some mixture of original field plus reflection. So reflection coefficient equal to 0, it's also important in order to see what you want to see without any modifications. All right, and the idea was to create some other metamaterial and some other concept which can give us this operation as a perfect transmission device. As Misha was telling to you, you can stop me at any moment and ask any questions. So if you wish, yeah, just whatever, raise your hand or just interrupt me. It will be not bad at all. Okay, so idea is the following. Let's change the mother nature in this sense that vacuum is actually not the best material. In the vacuum, you have propagating waves from one side and evanescent waves from the other side. Yeah. So in terms of the wave vectors, it means that as soon as component, say ky of the wave vector is smaller than k0 equal to omega divided by c, say for vacuum, then this wave will propagate in the free space. But if ky, say, will be greater than k0, then kx will turn out to be imaginary number and the wave will be decaying. These waves are called evanescent waves. So in this sense, for diffraction limit, this is a major problem, that you have separation for propagating and evanescent waves. So solution is very simple. Let's kill something which is bad. In our case, evanescent waves are bad because they decay and lose the energy. Idea is let's have metamaterial without evanescent waves at all. So if we don't have decay of fields, we will not lose any information. If we lose no information about our image, we will have great chances to restore it at some distance. And this is simple idea. So we need to construct, design a metamaterial with completely flat isofrequency contour. So we need something which with propagation along x direction kx, which do not depend completely on transverse wave vector ky. So I will show you some examples how we can create such metamaterials, at least 1, 2, at least 3 examples how we can do it, yeah, but a little bit later. let's imagine that we do have such material. So if we take some information is coded in special oscillations of field. If you transfer this into the Fourier space, it's stored in amplitudes and phases of the waves, which can travel in different directions. Yeah. So now all these waves are changed, to kind of modified into the eigenmodes of these metamaterials, and they will be traveling along fixed direction, along x direction, because group velocity for any point of this flat isofrequency contour is directed along x. So in this material, there is no diffraction at all. So all waves are traveling in one direction. And the phase speed of all waves is the same. They're traveling with some speed kind of along x, independently on ky. So if we have such material, then we can create a perfect transmission device by just using a simple idea which we know from basic optics, Fabry-Perot resonance. Fabry-Perot resonance, in conventional dielectric, you have a slab, you can make certain conditions at which you will have a perfect transmission of light through and no reflection. If you have no losses inside, you need to fulfill a requirement that the thickness of the slab is equal to integer number of half wavelength, and everything will be fine for this Fabry-Perot resonance. But as soon as you change angle of incidence, Fabry-Perot resonance condition stops to hold. Yeah. Luckily, over here in metamaterials with flat isofrequency contour, the speed of light across this material is the same independently on transverse wave vector. So Fabry-Perot resonance will hold for all angles, independently on angle of incidence, including complex angles of incidence and real ones. You will have Fabry-Perot resonance, and you will have total transmission through the slab. And what you have to do, you have to properly choose the thickness of the slab to obey this Fabry-Perot resonance condition, and do not forget to orient your flat isofrequency contour properly. So your light would be crossing your slab, not just traveling in some other directions. And in this case, your slab will be completely transparent. So basically, you can place your source next to this slab, and all fields created by the source will be somehow channeled or canalized by the slab. So the field, without any reflection, will enter to the metamaterial slab and will travel as basically as a plane wave, in a sense, from one side to another side. And at the other side of the slab, you will get an image without any distortions over here. You see that this source do not even feel that something is going on around. Yes, so it's it do not experience any reflections and create kind of channel which is coming from one side to another side and form an image at the other side of the lens.
There is a question from Georgi, and it says, what do you mean by complex angle of incidence?
Oh, yes, very simple. Yes, so so basically, as soon as you have components of the wave vector, say kx and ky, you can simply write down the formula for angle of incidence. We used to have it real one, but as soon as you have evanescent waves which decay, you have a complex angle of incidence. Yeah, and this is what I call then, say, ky component is greater than k0. So it's not real angle of incidence, it's complex, because if you take a look at the angle, yeah, it will be complex number. It has no real physical meaning, yeah, so you cannot associate with something, but you can say that this just corresponds to ky greater than k0. So there is something else in the chat?
No, it says okay.
George is happy. All right. Okay, great. What you also need to see over here, so over here there, I'm showing by my mouse the location of the source. In free space, you have some complex dependencies of the near field. near the dipole source. Yeah, you have near field, far field regions, so on and so forth. In this metamaterial, the flat isofrequency contour, there is no near field, there is no far field. It's the same field everywhere. You cannot separate it, and actually there are no evanescent waves, nothing which can decay at all. Yeah, so all waves are traveling with the same speed across this layer. Okay, this is a principle, looks a bit unusual, but we were able to realize it. And before we started to realize it, we took a look at something which is available in our Mother Nature in America, in UK. The people are calling this mineral as a TV rock. And actually, in Russian, they know it as incid. And this is a natural mineral, appeared because of the volcano activity or whatever other activities of our Earth long time ago. And actually, it's a bundle of optical waveguides parallel to each other. You can polish this stone like this. And if you take a look through it, you will see nice images of what you have below. For people who are actually interested and may approach me, yeah, I have actually this piece of incid at my table. If somebody after lecture will be interested, you can come and take a look at this. But this is not a mineral, this is artificial TV rock made by the people from Optical State Institute, but based on the same principle. So optical bundle of optical waveguides. This is very nice thing, gives us a hint. So if you would like to have an image from one side to another side, you need to have some waveguides which will pass this information from one side of your lens to another side. Over here, this is optical waveguide, which is pretty large in terms of the wavelength. It doesn't provide any sub-wavelength resolution. So we do need a waveguide with sub-wavelength cross-section. Yeah, and this is pretty easy. So we know that just a pair of wires at any distance between of them, it's very good waveguide. And we've chosen this as the first sub-wavelength waveguide in order to create material. And material for sub-wavelength imaging is actually a so-called wire medium. It's just a parallel array of wires. It's a densely packed wires parallel to each other, usually with the same radiuses, usually in periodical arrangements. And what is interesting over here is that this is kind of material which was known for quite a while, but till 2003, nobody noticed that it's specially dispersive material. And this is extremely important for us because due to this special dispersion and this Lorentzian dependence of epsilon of this material as function of the wave vector along the wires, this material has flat isofrequency contour at any frequency. So you.
Oh, wait. I think there is another question from George.
Sure.
Yeah, Pavel. Yeah, thanks a lot. Sorry for interrupting. I wonder what is the thickness of wires comparing to the wavelength, since I'm kind of puzzled. If you have a wire which is thinner than the wavelength, then you have like an analog for quantum well, then you have like a wave that has like the edges which are coming.
Yeah, Gosha, it's coming in the next slides. Yeah,
okay, sorry, yeah.
You. But quickly answering, radius of the wires is much smaller than the period much smaller than the wavelength. But radius of the wire is still greater than the skin depth of the metal. So it's purely classical electrodynamics without any quantum effects. So it's just a perfectly conducting wire, if you wish. Yeah.
Okay. So yeah. Wire. Exactly. I was wondering about these losses, how you deal with losses.
Yeah, okay. I will show you some limitations because of that. Yeah, immediately in kind of 10 slides or so. Over here right now, it's very, very important that for this material you have flat isofrequency contour for any frequency. Because actually, usually in uniaxial crystals and other materials where you may have these isofrequency contours close to the flat, usually they appear at one frequency. So you first have to create metamaterial operating at particular frequency, and after that tune your device. It's a bit crazy. Over here, this material works at any frequency already, and this is fantastic. It's wide band metamaterial with properties required for subwavelength imaging, thanks to special dispersion. This is the key, one probably unique case when special dispersion helps with something, but not kill some effects. All right, so what you have to do, you take these wires, orient them properly, so they should be perpendicular to the interface of your imaging device. So they will represent, in a sense, ends of these wires will represent pixels, which will be transferred from one side of the lens to another side of the lens. Period will dictate resolution, and the length of the wire should be integer number of half of the wavelengths. It can be just half of the wavelengths, it can be million halves of the wavelength. It's up to you. But at the end of the day, you will get image at the other side. And we have seen at 2003 the similar approach for another polarization, for people for S polarization. But the people tried to create kind of magnetic wires, very good idea. But these magnetic wires made by Mike Wiltshire in Imperial College, next door in London, actually, like 2 subway stations from Queen Mary. But the problem here is that these rods had enormous losses. They were working at one resonant frequency. Every Swiss roll is supposed to be tuned for this resonant frequency. And you imagine you have, for example, you need 1 million of these Swiss rolls. Yeah, any PhD student will kill himself rather than doing kind of these Swiss rolls to operate at the same frequency. Quite bad approach, I would say. Yep.
I have a question myself. Can we get with what you had on the previous slide? Can we get a number of images if we have an array of wires with differing length, like with different n? So can we have an array of images at different distances?
Yeah, yeah. Actually, Misha, very good proposal. If you will have like a set of wires of certain length, and after that another set of wires with another length, you will definitely have images in both planes, if I understand you correctly, for sure. I haven't seen any works about this, but it will definitely work.
Also, George is asking about superlattice. I'm not sure what he means by that.
George, ask by voice, please.
I can't comment on that. I thought Misha was talking about superlattices. It's like lattice inside the lattice. But shortening single wire makes it like you want to somehow distinguish resonances spectrally, Fabry-Perot resonances spectrally by shortening one of the wire.
No, George, it will not work like that. They will operate at the same frequency, and images will appear in two kind of different locations. The problem is that these wires are usually not interacting with each other right at the resonance. And they will not actively interact if it's lambda over 2 and lambda wires. Yeah, so we'll have images in both planes, I would say.
Okay, thank you.
But still, this is my intuition because I was not doing this. Yeah, but they should be there. So you may have different images. And Misha, let's wait until the end. I will show you that you actually can move these images to the proper places by periscope-like geometries. I will show you some examples. Let me continue. Yes, so I was saying bad words about our colleagues from Imperial. They are very good guys because they were first who used metamaterials for MRI, but this Swiss rolls concept remained in 2003 and was never used since that time. We tried to model an array of wires. This is famous lens, 20 by 20 wires, 15 centimeters long. It will operate around 1 gigahertz frequency at microwaves. and P loop, letter P was used as a source. At that moment, I didn't know what I shouldn't put these two parts very close to each other at the distance which is nearly not be possible to resolve. Luckily, the currents were flowing in the different directions and I was able to resolve it. So what I've got, I've made a simulation in CST Microwave Studio, which appeared 3 years before that as a tool at all. And I have seen that actually near the front interface where the real antenna is located, there is a field in the form of the letter P. And at the back interface, I see exactly the same distribution. I was kind of completely amazed and happy with this. Took a look at the field distributions by amplitudes. And what I have seen ends of the wires, which dictates the pixels. And this was a first simulation of a canalization device working with resolution 15 times smaller than the wavelength. I'm pretty sure that today we have some people from optical community, and please confirm that I'm not lying, that there are no really lenses for the visible with resolution 15 times smaller than the wavelength. And this is the operating one. And actually, if you would like to make a better resolution, just make a denser array of wires. Resolution will be better. After this simulation, we decided to create a lens. This was again first and the last lens made from aluminum wires. After that, we used copper and bronze because we need to have a little bit harder metal. But first one was with this aluminum rods. We placed this P-loop antenna, scanned the field from one side and from the other side. At that moment, I was not really kind of good in near field measurements, but we have got the images at resolution 15 times smaller than the wavelength was confirmed. Yeah. And basically, field distribution in the source plane and the image plane are really non-distinguishable at these pictures, but believe me that they are done in the different planes. And at that moment,
what was the wavelength in here, or the frequency?
1 gigahertz, 1 gig. At that moment, most of the people started to ask me, okay, Pavel, you have this nice lens. It's operating at 1 giga. And what is the bandwidth of operation? I told, all right, yeah, you don't like my P-loop letter, which do not change the shape depending on the frequency. And okay, let's put something more complicated. I found I think the most complicated source ever I was using. It was meander source like that. We printed it on PC board, fed by coaxial cable, and measured it. It's quite resonant thing, but we identified the bandwidth about 5%, at which we have seen the image, and at which we haven't seen any difference for this antenna with wire medium lens nearby and without. Basically, the fact that S11 for the lens does not change with wire medium or without wire medium at this range means that there is no reflection at all from this thing. But also we have measured at different frequency ranges the fields, and we confirmed this 5% bandwidth, and we found some strange phenomena which we were not able to understand what are they. And finally, at the following slide, I will show you that in few words later we identified, but these are kind of surface plasmons, surface modes, which can travel in this wire medium slab at the interfaces. And as soon as you're coupled to this either surface modes or waveguiding modes, if you consider the slab as a waveguide, they drastically modify the images. So you should work outside of range of these surface modes, and then everything will be fine.
Well, Pavel, there is another question from George, I think.
Yep.
Yeah, Pavel, thank you very much. So I wonder what do you mean by term resolution? So you mentioned wavelength over 15 resolution. So can you distinguish like two objects which are located on the distance of the order of wavelength over 15, or how do you claim that your resolution is such?
Yeah, okay, good question. Take a look. Yes, so resolution definition is unique. Yeah, if you have two sources at certain distance, if you can resolve, then this is resolution. Yeah, you can distinguish two maxima. Alternative equivalent definition is you have a point, whatever source, yeah, like a delta function. You have some spread function, and half of the thickness of this image is your resolution. Over here, resolution is a period, and we see it because of details which we can observe. Say over here, we clearly see that over here there is a very tiny detail, which is just one period of the structure, and it's reproduced. And the thickness of this is about one period of the structure. Yeah.
Okay.
So mathematically, in the theoretical papers, we proved that resolution is actually in between of the period and two periods. So two periods, it's actually more than real resolution of this device. One period is something which usually people can see, because you also have near fields because of the ends of your wires. Yeah, that's why you cannot clearly say. But okay, if you're okay with two periods, then this is exactly lambda of the 15, which you will get here. Period is 1 centimeter, wavelength is 30 centimeters. So it will be two periods over here. Yeah, George?
Okay, so very weird scale, I would say, but I think, so you're trying to mention if the half maxima, the width of the half maxima allow you to distinguish two wires, this is called resolution. Okay, so over here, I think, yeah, it's kind
I will show you now, I will show you just a little bit, yeah? I will show you some more kind of nice images, and we will return to this, yeah, because the issue of resolution will be important in the presentation. Okay, let me continue the story, and we will return to resolution. So we decided to kind of make another lens, which is better looking, longer, heavier, and better operating. So we kept the period to be 1 centimeter, but took 1 meter long wires. We modified P-loop letter, which represented Pavel, and replaced it to crown, which was representing Queen Mary University of London, and made much better photo of the via medium lens inside of anechoic chamber. I like it very much. I spent about 20 minutes to get a nice photo and nice lights on it. But it was also good that it was working. We scanned again source plane of this nice crown loop antenna. We were scanning it without lens. We were scanning it with lens, both in source planes, and we were scanning image plane as well. The lens is long, and actually for around 1 giga, we've got 2 Fabry-Perot resonances. These were 6th and 7th Fabry-Perot resonances. So basically length of the wire was 3 lambda and 3.5 lambda respectively at these wavelengths. And over here you see images at both these frequencies. Resolution is reciprocally 17 times smaller than wavelengths or 14 times smaller than the wavelengths. Over here, accuracy of scanning was much better. And over here, you can really see in the image these tiny details, which gives you a hint about resolution.
Yeah. You mentioned that before that these super lenses, they allow say canalization of the source the field distribution without any distortions. But in here we can clearly see the blurring in the image. What is it related to?
Yeah, take a look again. There are no distortions up to resolution. Yes, so any device is working with particular resolution. So if you kind of pixelate your image at the output you will have exactly the same image as an in front. Yeah, but of course I'm showing you much more details. Actually, the resolution of this particular image is 1 millimeter, but resolution is 2 centimeters. Yeah, so I'm showing you much more details over here in order to have an idea what's going on. That's why we do see some blurry things over here. Actually, these are surface waves which are starting to travel, and over here you have some diffraction at the edges. Yeah, another question? Sergei, was it you?
No, I think it was just some interference.
Okay, no problem. I thought that Sergei wanted to comment something. He's also a very great specialist in these biomedium lenses. All right, when I move on, take a look. So now I will show you the images if you modify the frequency a little bit. If you're standing right at Fabry-Perot resonance, this is red frequency, 1038. You see very nice image at the output plane, no problem at all. But if you go a little bit low frequencies, take a look, few percents of the frequency goes down, you already lose your image because some blurry things appears over here. There are some ripples and maximas. These are these surface waves which are undesirable, but at lower frequencies below Fabry-Perot resonance, they do appear. And you shouldn't work below Fabry-Perot resonance at all. You should work right at Fabry-Perot resonance and a little bit higher. And at a little bit higher frequencies, there is no problem. You do have very nice images which reproduce everything. The usual bandwidth for these examples is about 5% to 10%, depending on kind of your original source. Yeah, because if you're not really kind of trying to identify resolution, but just placing some image, for you it's very hard to identify resolution at the end of the day. And you can only guess what is it. All right, so we've done this at microwaves. We were pretty sure that actually we can create any resolution at microwaves. There was a crazy idea to make 1 millimeter period lens and make extremely high resolution. But at that moment, there was already Nobel Prize for subwavelength resolution with fluorescent microscopy, and interest to subwavelength imaging somehow with help of metamaterials disappeared. So we decided that we stop this activity and do not do such crazy things. But we were thinking about some other frequency ranges. We immediately decided to verify what we can do in terahertz range. We simulated a nice lens with chalcogenide glass and silver rods inside with period about, was it 1.3 microns, I believe. And yeah, radius about 130 nanometers of the wire. And our simulation was showing that actually we can have very nice images in terahertz range. Much later on, it was 2012, 2013, our colleagues from University of Sydney created a bundle of terahertz waveguides and experimentally demonstrated that these terahertz lenses are operating. Returning back to resolution and to what George was asking at the very beginning, depending on frequency at which your lens is operating and depending on material which you are using for your lens, you have some limits in terms of the resolution because you cannot make radius smaller than the skin depth, and reciprocally you cannot make a period much smaller. So basically, if you're working at 1 giga frequency, you can have good resolutions which is 6,000 times smaller than the wavelength without any problem. I think the best resolution I was showing it was lambda over 300. And if you go to terahertz range, at 1 terahertz, you can think about resolution lambda over 200, which is quite good, I think. But if you go to the high frequencies, say 10 terahertz, you're already kind of coming to the resolutions lambda over 60, and so on and so forth. So a little bit higher frequencies will start to give you quite bad resolution. If you're approaching infrared range, we did our best to find something there. So the probably smallest radius which is possible for canalization in order to do not have plasmonic effects and have a lens operating really as a channeling was about 20 nanometers, period was 200 nanometers, and we have shown resolution lambda over 10 for 30 terahertz frequency. And right after that, our colleagues from group of Northeastern University in the US by Sridhar, they took porous alumina. It was quite popular at that moment to use porous alumina and fill the pores by metals. This was early stage of hyperbolic metamaterials, and this is very good and unique opportunity to create wire medial for visible domain. They filled this by gold, as far as I remember, took a quite large sample actually. You see, sample was really kind of comparable with US coil, and we have made experiment. They put a mask with these NEU letters and scan it from in like a diffraction of the laser beam at the other side of this mask. They've got this NEU at the other side, and after that they put this metamaterial nanolens and scan the image at the other side, and they got this NEU as well. Over here, wavelength was 1.5 microns, and resolution was 4 times smaller than the wavelengths. So it's already kind of sub-wavelengths, but already with immersion lenses, you can get something close to this. But over here, the distance between image and the source was 6 wavelengths, so kind of comparable to what I was doing in microwaves, but in infrared range already. So at this moment, we understood that, okay, there is no way to go higher frequencies with the same concept, and we need something else. So we actually estimated all possible kind of materials. There was a chance to use aluminum wires and go up to 70 terahertz, but it didn't help. So it's again infrared, nothing in for the visible domain. And they started to think about visible range, what we can do in the visible range. And in order to have a flat isofrequency contour in the visible range, they decided to think about materials with extreme optical anisotropy. So basically uniaxial media with, say, epsilon along one direction equal to something, and 1 and 1 along other directions. Depending on sign of epsilon, you either have elliptical contours if epsilon is positive, or you have hyperbolic contours if epsilon is negative. You have hyperbolic metamaterials if epsilon is negative. But right in between, if somehow by Lorentzian curve, whatever, you can get epsilon very large, close to infinity, then you will have exactly flat isofrequency contours which are required for canalization regime. And we decided to realize this. So just the idea is to have a material with epsilon equal infinity 1, 1 by diagonal. The easiest way by that time was to try to make it from metal-dielectric multi-layered structures. So it was quite popular to create them. And we also followed this trend. We consider it a slab of metal and dielectric. We used a simple averaging formulas. At that moment, we had no idea that this averaging is not really working, but we were lucky enough to work in the regime where these formulas are actually operating. We put an equation. So we decided to solve an equation that epsilon parallel is equal to 1, epsilon perpendicular equal to infinity. So basically, so this should be 1, this should be infinity. And if you solve this, you can have relations for epsilons of the layers and thicknesses. So first you're getting that epsilon 1 divided by epsilon 2 should equal minus d1 divided by d2, where d1 and d2 are thicknesses of the layers. This gives you a hint that as soon as thicknesses of the layers are real numbers, then either epsilon 1 or epsilon 2 should be negative. So you have to use dielectric and metal for the visible domain. And also epsilon 1 plus epsilon 2 should be equal to 1. Yeah. And it was pretty easy to satisfy, say if you have material with epsilon equal to 2 and epsilon equal to -1 at particular frequency, and ratio between d1 and d2 should be 2. And we performed modeling of the layers of some material with epsilon 2 and some material with epsilon -1, and thicknesses of the layers was 10 nanometers and 5 nanometers. And we've got very nice images. Of course, we drew the model for silver in this case, because silver was satisfying at particular frequency range with epsilon -1 condition. And we've got very nice image at the back interface of this device, quite nice. Right at the back interface, we have seen surface plasmons, which were traveling at the last silver layer, but at a distance about 20 nanometers, we've got very nice image, and resolution was 20 times smaller than the wavelength. So this was a realization of canalization principle for the visible domain, but at the same time, there was very strong competition with other groups, and in parallel, the group of Nader and Geta and Evgeny Narimanov, they were inventing in the same year, 2006, the Hyperlens concept. And they were using exactly the same multi-layered metal-dielectric structures for that purpose, but in the hyperbolic regime. Idea was to create a lens which take two sources, magnify them, and after that you use far-field optics in order to detect this. Actually, this supposed to work in canalization regime, but canalization regime was not invented, and people didn't know about that. They were using hyperbolic regime, but everything was more or less working as soon as these hyperbolas were very close to the flat isofrequency contours. The people were numerically getting images, and right after that, group of Shenzhen performed experiment with real silver and alumina multi-layers at 365 nanometers wavelengths. They put chromium needles, chromium rods in the forms on words nano and O. NA somehow disappeared, something wrong happened. Probably A was not distinguished. That's why in the science paper they put ON only. And this is actually image we have seen in the real microscope by eye, by conventional lenses at the output. But over here distance is 200 nanometers, so this is deep subwavelength objects. And after that there were many other papers when the people were using these multi-layered structures for imaging. Over here the major problem is losses in the metals and problems with accurate manufacturing of these multi-layered layers. In parallel, the same hyperlens, similar hyperlens was created with the grooves on the plasmonic layer of metal for surface plasmons. Yeah, and we were always joking over here. It's also science, and actually the same number of the journal Science, like 1-to-1, 2 publications. The problem is that at the publication of Shenzhen, all the people do see O-N letters immediately, but 3 maximas over here, only Igor Smolininov can see probably in his experiment, but they're saying that over here, yeah, there are 3 point sources, and these are the 3 images which they observed. Yeah. Depending on quality of experiment, but at the end of the day, Hyperlens concept is working, and it's partially based on canalization principle. What we did, we realized that Hyperlens is very nice, and we decided to make a Hyperlens for microwaves. We immediately put letter M For magnify, we performed simulation and FICO by method of moments because the system was too complicated to simulate in any simulator available at that moment. And we've got triple magnification with extremely nice resolution. And we were quite happy with that. We first published theoretical paper. After that, some competitor like Satoshi Kawata with Prabhat Verma proposed to use similar things with nanorods, plasmonic nanorods indivisible for color imaging. We spent after that quite a lot of time to show that this lens is not operating. We have like 4 or 5 publications demonstrating that it's not really correct. And the problem was that actually Satoshi proposed to use incoherent sources for imaging. And our lenses were working with coherent sources. Over here, it was claimed that as soon as you have incoherent sources, the image is getting better. But we have shown that actually it's not exactly so. And this lens is not really properly working. And there were no experiments demonstrating that this lens is operating. It was purely numerical kind of reasoning for this color imaging. But for microwaves, we have created our Hyperlens. Now we have 5 millimeters period in the front and 15 millimeters, 1.5 centimeters at the back. Again, crown as a source. And this crown source was magnified by this lens quite nicely to the output plane. And this was 3 times magnified resolution with lambda over 30 resolution and 3.5 distance between source plane and image plane. I think it's kind of a record for the distance of transfer and resolution simultaneously together with magnification by that moment. And also you could rotate the lens. We were rotating the lens and using it for demagnification. It's also quite important when you create some distribution of the field with not very fine details, but after that demagnify image, and then you can create very nice tiny details. Over here we again created large crown, scan it, and in image plane we demagnified this. And the minor problem over here was that actually for scanners in microwaves, we usually should use plane interfaces. And if you're creating these hyperlenses larger, then you already cannot fulfill Fabry-Perot resonance condition over here. So basically length of the wires in the corner of the lens is no more equal to the length of the wire in the center of the lens. And this is problem. You're getting disturbances, you're getting Fabry-Perot resonance not everywhere in the lens, and so forth, and other problems related to this. But we solved it because the waves traveling through wire medium, it's just the plane waves, and we put a piece of dielectric inside, which was compensating the phases, and electrical length of wires was exactly the same. So physical length of wires was different in the different locations of wire medium, but electrical length of wires was the same. With piece of dielectric, we've got very nice images, and we were able to solve the issue of making larger areas of magnification and so on and so forth. Over here we have 10 centimeters in the front and 3 centimeters at the back, and everything is working for the same frequency. All right, and then finishing, I would like to show you a few slides that actually you have seen that we can transfer images with subwavelength resolution, magnify, demagnify, but we also can shift images. For this purpose, we may use periscope-like arrays. You will need to move your wires towards some directions, like you can see here with the periscope. It's very important for terahertz imaging, because if you have terahertz waveguides and you would like to somehow change the shape of the waveguide, you can do it, as you can see. And at the end of the day, at Fabry-Perot resonance, you will get the nice image. You will have distortions of images which are different as compared to the normal planar lens at other frequencies, but at Fabry-Perot resonance, you will have the image as it should be. I see some questions.
Yes, there is a question from Ivan about what is the critical bending angle, and I guess if there is a critical bending angle.
Yeah, Vanya, very good question. There is no critical bend angle, so you basically can turn 90 degrees at any angle. You have to properly turn, so you have to cut the wires by certain angle, and another set of wires should be the same angle. So this is not correct actually bending right now. And there was nice advanced materials paper by Shanhui Fan right after that, when he was showing the right bending. I did know this bending as well, but I gave it to Alex Agejski, you know him very well, and he didn't succeed to write a paper and finalize this. Yeah, but bending angle is arbitrary. Yeah, this is true. Thank you for the comment. Probably you know this and just raising this as important issue. Thanks, Vanya. There was a second question, no?
No, I think there wasn't yet.
George again writing some corona. Okay, yeah, corona, exactly, yeah. Corona was detected, you're correct. So this is one of the last slides. Again, you remember that we are back in time, so it's 2008. So Alexei Slobozhenyuk was not yet done his first experiment in MRI, and even Christophe Crayer with Radu haven't started their experiments in MRI. So we guessed that these near-field endoscopes may find some applications in magnetic resonance imaging. I think right now our group, with the help of our French colleagues, really demonstrated that we can use similar structures for MRI, not exactly the lens itself, but at least resonators with Fabry-Perot resonances, which were kind of used in these lenses. Medical terahertz imaging, this is something which we people from Sydney are doing, and they're actually claiming that this is extremely important. I still believe that there is a room for optical near-field microscopy applications based on this, but somehow interest to this disappeared. Again, I'm returning back to some other techniques of subwavelength imaging which were invented for biological objects, like, again, fluorescent microscopy. So people are just using other methods, not simple optical microscopy. And as we know, actually, there was a guess that probably optical drives with increased capacity can be created based on this. Luckily, optical drives just disappeared during that time, and there is no reason to do them at all. And there was the idea that some nanocircuitry, metatronics, and ultra-compact optical components based on this can be invented. I'm not sure that it has happened. Probably the most important results still appeared at terahertz and microwave range, not in visible and not in optics. And I came to my conclusions. So basically, idea is that it is possible to get lenses with subwavelength resolution and transfer images with subwavelength details to significant distances in all possible frequency ranges. Depending on frequency range, you need to use different materials. And you can magnify, you can demagnify, you can shift and bend your waveguides, and everything is working. And if you are interested in some details, I just refer to our overview paper on metamaterials we published again 8 years ago, 2012. There we've got some details. There are new results which we obtained with Sergei Kosulnikov, Losha Slobozhenyuk, and Polina Kapitanova, and Dima Filonov. They are not included into this presentation because they were obtained a little bit later, and they're also kind of quite nice. So if somebody is interested, you may approach me and I will give you some details. Thank you for your time. Yeah, and I will be happy to answer some questions. And Sergei wrote some something in the chat. Yeah.
Yeah, Pavel, thank you for your presentation. I think you mostly answered Sergei's question, because what he asked is that when you're now in 2009 and you're looking at what you're expecting from metamaterials, so what are your expectations? And you basically listed them just recently. But so what are your probably current expectations, and what provided that change in the expectations throughout those years?
Yeah. I will tell you. Yes. So during that time, the interest to metamaterials dropped down quite significantly. As all we know, kind of the interest to meta surfaces appeared because these are structures easier to manufacture, and the people are manufacturing meta surfaces for the visible. That's why focus of Sauron eye moved away from metamaterials. But I believe that all science is going by the spiral, and metamaterials will definitely return. I personally experienced at least 3 turns of these spirals, and as far as I know, there are at least 5 for artificial materials, bioisotropic materials, photonic crystals, metamaterials. So I think the new one will come, and I would like to say that maybe the next turn of metamaterials, or whatever artificial materials structures, and partially related to imaging, subject imaging, will appear with specially dispersive media like wire medium. Yeah, because previously in 2000, 2005, people were thinking only about left-handed media, something which the people understood, and they were using local epsilon, local mu, and were not able to create a perfect lens. Yeah, and probably with some kind of like proper materials, like especially dispersive materials, without losses, it will be possible to do something nice. I think the people from optical community did a mistake that we do not continue to study the extremely anisotropic metamaterials. I was actually talking to Anton Samosev. If he is not here, probably he is not here, and showing that actually material with epsilon infinity 1,1 in the visible is possible. You just need to take some uniaxial material with Lorentzian curve, whatever peak of absorption. And as soon as in the material you will have a peak of absorption, you will have, without losses, canalization of images right at this frequency. This is a little bit strange, yeah, but it will happen. This was never confirmed experimentally, but I believe it will be working. So definitely it can be used, Sergei, in still perspective. I have to say that actually one of the direction is direction of your supervisor, Konstantin Simovsky, with control of temperatures and actually infrared and terahertz emission. This is really a very interesting direction where these lenses can find very nice applications. And bio applications in terahertz range, which I was mentioning over here, I think also this is still there. So this is still very important. And I know that it's very hard to approach some places inside of the body of the human for terahertz imaging, and terahertz endoscopes can help with this. And even for MRI, still endoscope on flexible wires can be useful, yeah, say for scanning somewhere deep inside of us, some areas, yeah. People forgot about this approach, but I think it's also kind of possible. So applications are very similar to this, with emphasis on terahertz imaging.
Thank you. So we have a question from Oleg Yermakov, I think, which was first, and then there is a comment from George.
Yeah, thank you, Pavel, for very exciting talk and yeah, very interesting story and results. But can you explain why the wire medium has flat contours at any frequency? So what are the physical origins of it, and how can you prove it? I didn't get it.
Okay, this is coming from the fact that a pair of parallel metal conductors supports TEM wave. It means that as soon as you have pair of conductors with some currents flowing, you can put third conductor, and this conductor will be polarized across, and there'll be no current in this conductor. It means that you can place any current in third conductor. So this is in a sense physical explanation why you don't have dependence of dispersion properties of wire medium on a transverse component of the wave vector. And this is true till the moment then the metal is ideally conductive. Yeah. So in this sense, it's wide band and kind of up to terahertz range. Wire medium has this flat isofrequency contours. Right after that, already in the infrared range, there are many works of Konstantin Simovsky, Mario Silverinia, but instead of flat isofrequency contour, you have flat plus hyperbolic isofrequency contour, and then my statement becomes not correct completely.
So in this sense, there is some sense to say about, I don't know, dispersion or something like this in this case, or
what kind of dispersion, Oleg? What do you mean dispersion? In which sense dispersion?
I mean the dependence, the frequency dependence. So nothing depends on frequency in this case.
No. You have formally you have material. Okay, if you don't want to speak about special dispersion, you formally have material with epsilon equal infinity in one direction, and epsilon equal to host material epsilon like 1 or whatever 2 in other direction. So they do not depend on frequency at all, and frequency dispersion appears only in the infrared range.
Yeah, okay, I see. Okay, because indeed for any other system, it's impossible to, so usually a canalization means that, yeah, you have extremely large, yeah, for instance, permittivity in one direction and 0 or even near 0, yeah, in another one. But it's obviously, it can be achievable only in the very narrow range, or strictly speaking, at the single frequency, yeah, okay.
Yeah, well, Oleg, as you can see here, yeah, I was not hiding anything. Yeah, for wire medium, it happens at any frequency. This is a feature of wire medium. For multi-layered structures, yes, it's one frequency. Yeah. But over here, it's so. Also, if you have mentioned actually the fact that there is a canalization with epsilon 1, 1 infinity or 0, 0 infinity, yeah, we were fighting with the guy from Czech Republic who was also comparing this. Actually, this 0 is really not important. So you can have 1, 1 infinity and it will be working. Just Pendry was using equal thicknesses in the first paper. That's why somehow 0, 0 infinity for multi-layers started to be used. But it's useless. 1, 1 infinity is much better.
Okay, thank you.
Okay, so Goshak, can you comment on what you wrote in the chat?
Yeah, sure. So Pavel, you mentioned that there were some attempts on, like I would say, adopting this phenomena to optical frequencies in the optical range. So can you comment maybe on some works of Anton that were using near field optical microscopy? Well, basically, I think this is the similar concept where you're using just a plasmonic, not wire, but tip, which also has some, I would say, waveguiding properties, or maybe some other Sergei Bozhevolny works. Maybe you know why he stopped working in this field on this probably imaging in optics. Maybe there were some deeper, I would say, drawbacks, major drawbacks, which.
George, there were no really drawbacks, as I was mentioning. There are just other techniques which allows you to get images of what you need. Yeah. So basically, with electron scanning microscopy, you can get resolution up to 1 nanometer. Yeah. There is no reason to play with optics in order to get kind of some other resolution. This is probably the point. So just other technologies were quite rapidly developing, and that's it. At the same time, for biological purposes, this subwavelength imaging in the visible is still needed. And I was working with some guys who are doing really medical imaging. They were extremely interested in this. But again, it's not a matter of snow, yeah? So it's a matter of really device which is operating, and nobody made a device which is operating. And probably that's why the interest disappeared. I think it's also was dictated by the fact that interest in all plasmonics started to drop down, and as a result, interest to this activity also dropped down.
Okay, I have a question myself. I think there are no more, no one else then. So if you, I have a question about that demagnification device. So my question is about the power transmission through this, because I'm wondering if you have, for example, many sources, many power sources at the source side. How will the power combine at the image plane? Can you say have sub-wavelength heating at the image size?
Brilliant, brilliant, Misha. Thank you very much. Actually, there was a project, I forgot to mention this. Yeah, my friends from Hyperlens University in Scotland, they were using my lens for millimeter wave range for soldering purposes. They had a problem. They were using microwaves in order to melt metals. And always there were some issues with small gaps. Somehow they were replacing all this stuff and nothing was working. They found me. I told them, make this demagnification lens and everything will be fine. Just be sure that your wires will not melt. And they really created this demagnifying lens, which you see at the screen, but for millimeter range, and made an operating solder. I think they were even selling this to somebody. I lost the trace, should be checked. In terms of the energy, this is kind of power. Power is kind of kept here, yeah? So nothing appears, nothing is lost. Nearly there are no losses in the wires over here. Its losses are very small. So intensity of the light at the output is the same like at the input. The point is, it's not about kind of power radiated by something. You have to take a plane. If through this plane you have some power passing in the image plane, the same power in the source plane, the same power will pass through the image, but the power will go through smaller area. And in this sense, indeed, if you would like to make high intensity at the output, yeah, make 10 times demagnification device, and intensity of light will be 100 squared times higher at the output.
Yeah, this is interesting because what I also thought about is using the canalization principle for maybe detecting brain activation signals, and those signals are very, very tiny, and the frequency, I guess, would be very, very low, maybe kilohertz or something on that range. So now it is done with some weird magnetoencephalography devices, which are pretty bulky. Maybe you can use some optical magnetometers now for that. But if you like move, can you move away those signals from the head and maybe build some better reception device somewhere on the side? But that requires very, very low losses. You always say that the wires do not have much losses in there, but what about very, very low signals? Will this work with that?
Take a look. Yeah, of course you will have temperature noise from the wires.
Mm-hmm.
But luckily it will be incoherent. So if you have a coherent signal, yeah, then you will be able to detect it at the out. But at the end of the day, I think it's really good idea. And Misha, I mean, we can talk about this a little bit later and kind of design something. There is also unique thing for kilohertz range, which the people were never using. I was selling it to many guys, but nobody was kind of trying to do it. There is Fabry-Perot resonance of the zero order. You need a zero thickness and everything will be fine. So for kilohertz range, you don't need to make a kilometers length. You can really make this length particularly. It will also work at the zero wavelength. It will concentrate what you need. We just have to put your head at the left side, and this was 3 times by 3. Okay, 100 times more intense field will be at the output. So if it helps somehow, okay, let's just take this lens, put receiving whatever antenna at the image plane, and that's it.
I just realized that there might be an interesting application to that, because at least in the sense of increasing the number of channels in ECG devices which need a lot of channels, and maybe their sensitivity now is limited by how many actual receivers you can place on top of your head. Maybe if you use some demagnification length and you can put them say magnify the head of the patient multiple times, and that would allow you putting a lot of the sensors in that case. I think there is some question, some comment from George again about super resolution bioimaging, right?
Yeah, sure. Just a comment, not a question. So I think I partially agree with Pavel. So like scanning electron microscopy developed into like a huge industrial, I would say, area. And which is maybe even more important, that conventional optical company, which is called Carl Zeiss, they decided to create such scanning electron microscopes, and instead of maybe non-linear microscopes, full optical. So yeah, for sure, maybe this is the answer for the comment that Pavel stated. But to be fair, there are some papers on non-linear optical imaging in bias cells, and both are published in late 2000s. So
yeah, but this is exactly fluorescent things which I was kind of mentioning. Yeah, the fluorescent effects. Yeah, you can have very nice resolution. This is this Nobel Prize of Stefan Hell.
Yeah, this is like a donut shape with a Gaussian shape. Yeah, exactly.
And also, this is another story. Yeah, you know, kind of. For some applications in biology, yeah, it can be still quite useful, because you cannot afford to go inside of many tissues by kind of electrons, whatever, but you need some tiny information about tiny details, yeah? And with transparency windows, you still can go there, but you need near field access. So it's still kind of, for all these things, your lenses should be in the near field of the object. And this do not help a lot. Yeah, you still have to approach biological tissue, and it's not that easy.
Oh, okay. So thank you. I don't see any more questions. So thank you again, Pavel. I think we would with this finish our seminar today.